Alright, guys. Let's get to work then. Those graham crackers made me feel better. We're going to be using this little buck converter chip. Costs like 40 cents on eBay. We have to solder 4 wires to it to use it. Alright, positive on the top. Got it. I sure am. I'm working on fixing my laser printer. Still. It's the project that never ends. No matter what I do, it just keeps going and going. I need 4. Okay. First step. Oh. I guess we need to do this from the bottom. Eh. Well, that went well. That went too easy. Something bad's gonna happen to me. I know it. Nothing can be that easy without a catch. Something bad's gonna happen. Yesterday, within the first 20 minutes of starting electronics, a part exploded. It scared the heck out of me. Tell you what, this is going scarily smooth. I don't know what to make of it. Surely I'm doing something wrong. Let's be real. Ooh. Thanks for the resub, Need for. Everything's so easy when you use trimmed wire. They already did all the wire stripping. Pre-stripped. And my soldering iron was thoroughly cleaned last time before I left. And tinned, so that helped speed things up too, I guess. Those little factors are starting to add up to help me. Okay, so here it is. This needs to move the heck out of my face. Alright, so this is my buck converter. We got 2 wires in, 2 wires out. And here's the back of it. My soldering looks pretty good, I think, for the most part. It's not like dry joints or whatever. I think I use close to the right amount of solder. I mean, I don't know if it's perfect, but it's definitely functional, and I don't think anything wrong with it. Slightly sloppy, I guess, but I don't think soldering needs to be an art form, honestly. Okay, what's next? Solder 4 wires into buck converter and connect those 2 quick connects and connect that to jumper wire and connect 2 of those jumper wires to the 24 volt input and connect the other 2 to 5 volt output, which needs to connect to the switching MOSFET, which is to power the motor. I don't even know what I just said. Sounded complicated. Let's see. Has anyone ever donated Bitcoin? No. Make sure to use your invention for soldering? I didn't invent anything for soldering. Oh, wait. You mean this... the silver soldering idea? Oh, the fan! Eh. I prefer to get cancer doses. Builds character. How long for my arm to fully heal? Like another 4 months. I guess I could use it. I need it more automated. Having to press this thing down and then turn it on is kind of a pain. Uh... Alright, let's get out the quick connects. These quick connects are amazing. Okay, so, this will take 24 volts down to something. Let's see what it'll take it down to. Alright, so this is the input side. We need to connect this to our 24 volts. But how? I know how. Alright, let me get a male to male jumper in red or orange. Is this orange or green? That's green. I wish I had some red ones. What the heck? Alright, found one. Okay. There's the red. What the heck? Okay. Uh... Let me get a black. Male to male. Alright, here's one. Uh-huh. Alright, so this is all set up now. We could plug it in, and it should be okay, I guess. This is sketchy. I'm scared to plug it in. Are we good? I'm double checking, man. This is 24 volts. Gonna get myself killed. You might see an explosion. I'm following all the wires. They all seem to be plugged in. I don't see anything touching anything it shouldn't be touching. I think we're okay. I'm going for it. Ooh. Alright, I don't see any explosions yet. Maybe we're okay? Gosh, I'm like scared of electronics now. Anytime I plug something in, I just expect the worst. Alright, I need to test this thing with the multimeter and see what we're dealing with here. Yeah, yesterday a capacitor blew up. And it was very loud and scary, and smoke went everywhere. Okay. We got 13.16 volts. Close window. Stop listening. Alright, so we want to turn the little screw, I guess. The screw adjusts the output. We want it to be 5 volts. It's going to power our motor. I've never made a pipe bomb. I researched how to make a ball mill using a pipe. What the heck? What kind of screwdriver does this thing require? Alright. What is going on? What did I do with the pipe thing? The pipe thing is a ball mill. It's supposed to be a pipe that spins around bearing balls. I got the pipe. I got the balls. The bearing balls drop on little bits of metal and crush them up. That's it. Maybe I can use a flathead screwdriver to turn this thing. Alright, I just turned it 90 degrees. Let me turn it a little more. Ooh, I turned it all the way to the left. What's going to happen? So a flathead is all that worked for me. I turned it all the way to the left. $17. Okay, so we need to turn it way to the right. Wonder if we could like... No. I kind of don't want to turn it with it plugged in, but... Yeah, let me unplug it. Alright, let's try that. $8.49? The heck? That's gotta be it. $5.38. That's good. I don't pull all-nighters to finish projects. You wish I did that. But that ain't how I work. Maybe in my college days, but I'm more disciplined now. I think even pulling all-nighters is lack of discipline. It just means you're getting overexcited or something. Oh, 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 oh. Okay. Solder 4 wires in a buck converter and connect those two quick connects and connect that to jumper wire and connect two of those jumper wires to the 24 volt input and connect the other two to a 5 volt output, which needs to connect to the switching MOSFET, which is to power the motor. Okay. I need to set up for my shoulder right now. So we're not using the 5-volt regulator anymore. You can pull that out, as well as the capacitor with that, and the other capacitor, and this. Okay. Alright, let me think this through. Oh, I'm in it now, boys. I'm hooked. I'm invested. Once I start a project, I can easily keep going. I have to get into it. Alright. Power goes from the 5-volt power supply. Stop listening. Into the center of the switching MOSFET. Center pin. Okay. Then the right pin of it goes off to whatever you're powering. Now the ground just comes from the power supply directly to your motor. So here's the motor. Except we're not using the motor. Instead, we're using a light for now, instead of the motor. That'll do it. Now, if I plug this thing right in right now, what would happen? It's 5 volts to go to the center pin of the MOSFET. and nothing else. And since that MOSFET's off, nothing would happen, but if it's switched on, its right pin would get the 5 volts, send that to the LED. The LED would go through the resistor back to the ground. Light would come on. Okay, so I can plug it in, nothing will happen. I hope. So I'm putting away this component, this capacitor we don't need anymore. And the ceramic capacitor we also do not need. Alright, the next thing we're supposed to do is get the motor speed locked in how we want it. So that's the next job. Alright, let's plug in the Arduino. Our circuit will go live then. All the lights should start flashing. Everything looks okay. Alright. I want to get the motor involved now. Oh my goodness, look at that. Guys! Intelligent control of a motor! What have I done? Intelligence! No, I didn't break it. I don't have it turned on. I have it set to pulse in my code. 10 beats. It turns on for 100 milliseconds, turns off for 100 milliseconds. Does that 10 times. And then it pauses for like 3 or 4 seconds. That's all coded in. I could just turn it on full bore, but I'm trying to control its speed. So to control its speed, I want it on, off, on, off, on, off at a certain rate, and that way I can have fine control of the speed. It's working! Ah! I already cleaned my room today. Are you getting a return on your investment in this project? Yeah, the educational experience, and it's really a nice start to finish kind of easy project with microcontrollers to build up my confidence and hands-on experience to help me close the project with the switch mode power supply design. Alright guys, up to programming now. I need to slow it way down. If I can. Wake up. Code to turn a DC motor slowly. Press return. Maybe I have some notes on this. Stop listening. This is something I really should have notes on. That's not turning with enough force, I think, to adequately encourage the printer to turn on. The speed doesn't matter. It's a very weak motor. It's going to turn very slow, or not turn at all, really. It's just going to be pulsing a little bit of power at the printer. Press return. Press return. Wake up. Duty cycle, comma, frequency, comma, hertz, comma, press E, press Z, press Z, etc. Explained. Press colon. Press return. Press hyphen. In the above chart, comma, duty cycle, press space, press hyphen, press space. In the above chart, comma, we have a duty cycle of 50%, which means that, press return. Our motor would be running at half power. And by this, we mean press return. At half current, press semicolon, press space. I equals V divided by R. Press equals sign, press space. And our voltage is fixed at 5 volts for a 5-volt motor. Press delete, press delete, press return. So cutting the on time in half cuts the amps in half. Press return. And so in effect, comma, our MOSFET here would be acting as a resistor. Press return. With a value of 2, as it is cutting voltage in half. To give an amperage of 2.5 amps. But the inductors within the motor and the load on the motor creates additional resistance. So the actual amperage would actually be lower than that. But the point is that we are able to cut amp flow in half by only having the MOSFET switched on half the time. And we do this instead of using a 2 ohm resistor rated for a high watt flow that would get rid of the other half of the amps as heat, which would be very inefficient. Press return. Press space 10 times. Press semicolon. Press Ctrl S. Frequency. Measured in hertz, comma. Frequency is defined as the starting point of a cycle till, press return, press space 10 times, the ending point of that cycle, which is just before the next cycle begins. Press semicolon. So this can be measured peak to peak, or it can be measured starting with 0 in time, comma, including the rise to fully on for the MOSFET, comma, the fall back down to off, comma, press return, press space 10 times. The duration it is kept off, comma, kept. And then just before it is switched on again, comma, which would mark the start of the next cycle, comma, we mark that as being the end of our frequency cycle, semicolon. I indicated the start and end of a single cycle of switching on and switching off just before the next switching on as arrows in the chart above. If we have it on for 100 milliseconds and off for 100 milliseconds, comma, we would have a 50% duty cycle and a total frequency length of 200 milliseconds. The problem with this is that while, press return, it is off for that 100 millisecond pause, comma, it is not providing any power to the motor, press return, and the motor would just give way under its load or be doing nothing at all, press semicolon. And the goal with any motor, PWM pulsing, is to have the motor always outputting near the same amount of force on its load without jerkiness. Press semicolon. In our 200 ms frequency example, comma, we have a lot of jerkiness to the point of the motor completely stopping between pulses, which is ridiculous and unacceptable for any real-world use case. Press return. The hertz of household AC electric, comma, which is considered very slow compared to modern high-speed digital circuitry, comma, is 60 hertz, or 16 milliseconds. Press delete. Press semicolon. Compared to our 200 milliseconds in our example. But even that is quite slow for maintaining constant torque with our motor. Press semicolon. In order to have consistent power, comma, the frequency has to be high enough to where the inductors that charge up within the motor do not have time to fully discharge during the off cycle of the PWM frequency, and they continue to push on the magnets and keep the motor turning, even though the MOSFET has turned off some time ago, comma, it takes a while for the power within the inductors to dissipate. And so we just need to make sure to switch back on the PWM MOSFET before the inductors have gone beneath, say, half power. Press semicolon. On the other hand, comma, you also don't want to switch off the motor MOSFET until the inductors are fully charged within the motor. So you need at least a fraction of a second of on time for that motor to get fully charged up to the voltage level you are pumping into it. And this takes a while for the inductors within the motor to charge up that much. Press semicolon. And from some calculations I've seen online, comma, it appears that the inductor takes between 1 and 3 milliseconds to charge up to full. And so supposing we had a 50% duty cycle, comma, that would be 1.5 milliseconds on and 1.5 milliseconds off for a total frequency period of 3 milliseconds, which is 333 hertz. 8 megahertz to hertz. In. Press return. And with the @tiny85 having a clock cycle of 8 megahertz, or 1 hertz is 1,000 milliseconds. 8 million hertz, then 1 is to 1,000 as 8 million is to what? It's 8 million times 1,000. If 1 hertz is 1,000 milliseconds, so F, press backspace, press backspace, press equal sign. One, undo, press 1, press /. 200, press M, press S, press delete, press times, press star, 1000, So, to have a 50% duty cycle and a 2 millisecond frequency, comma, PWM, press delete. We would want 8,000, press return. Microcontroller cycles or 1 millisecond with the MOSFET switched on and press return. 8,000 microcontroller cycles or 1 millisecond with the MOSFET switched off. Press semicolon. Then if we wanted 80% duty cycle, comma, we would have 16,000 total cycles, mark, our 2ms frequency, 2 millisecond. Press delete. And 80% of those would be with it switched on. So 12,800 microcontroller cycles of on time and 3,200 millisecond program cycles, press comma, with the microcontroller switched off. Press return. Press semicolon. Now supposing we wanted a 1 kilohertz frequency for the motor and a 10% duty cycle, comma, so we have one full frequency cycle being 1 millisecond long, and since the has cycles in a given millisecond, comma, we know that the total on and off time of a single switch on and switch off cycle will take 8,000 microcontroller cycles. And since only 10% of that time it is switched on, comma, it will be switched on for 800 microcontroller cycles, and switched off for 7,200 microcontroller cycles. And this matches up with the microseconds in the code example above. Since 1,000 microseconds equals 1 millisecond, and they have the on time set at 1 microcontroller cycles. And the off time delay they have set at microcontroller cycles. Press semicolon. Note that to decide on my numbers for my laser printer, motor, PWM, comma, I will go under the assumption that since the motor is so small, it will only take to crank it up to full power, and then we just solve for how long we want it to be kept off. So let's say, let's say 60% duty cycle, so 40% of the time it is off. Is desired, so it doesn't overpower the laser printer. Press return. Or damage the belts, or burn itself out. Press semicolon. Microcontroller. Wake up. Microcontroller. Microcontroller cycles. Press return. Would be the cycled on time, and microcontroller cycles would be the cycled off time. Press return. Press semicolon. Wake up. Press semicolon. So it seems to me that 769 Hertz is a pretty good, press return, baseline frequency to power our motors with. And if we notice too much vibration and shaking, press return. We can increase that frequency to make the torque smoother. Press return. And more consistent. Stop listening. Let's go ahead and implement then. Wake up. Alright guys, this is a 60% duty cycle. We're going to plug in here. Let's see, we got our 24 volts, bucked down to 5 volts. That goes into our switching. Our light as well, and our switching MOSFET. Everything looks good. Motor's getting its stuff. Okay, everything looks good. So I'm gonna upload this new code with 60% duty cycle at 700 hertz. Alright guys, here it is. It's working. Notice the jerkiness is gone, it's now smooth. Unlike before when we had it at 100 milliseconds on, 100 milliseconds off. Now we have it at 0.8 milliseconds on, 0.5 milliseconds off in pulses, so that it's running at 0.8 on, 0.5 off, so that's 60% duty cycle. So we can make it go a lot faster than this. It's running at 60% power. We could bump that up higher just by tweaking our values there to have the off time be less. We'll leave the on time at 6400 microcontroller cycles, or 0.8 milliseconds. But the off time we could make shorter in order to increase the duty cycle. And I don't mean off time as far as like time between this thing turning on. I mean time of the pulsing on and off. It's just on, off, on, off, on, off, on, off, off, and then it's off. And then it's on, off, on, off, on, off, on, off, and then it's off. So that pulsing on, off really fast, we could have it on more of that time to make it more powerful. But we chose to make it only 60% of its max power in order to protect the motor from overworking and make sure the motor's going as slow as we can get it. Actually, we could probably make it even slower. But the speed of it is going to be affected by the load when it's under load. I want to try to hold it. Huh. We should probably increase that strength because it's weak as hell. Uh, yeah, I don't think that's gonna do jack squat. Um, if it's 6,400 and 2,000, it'd be 80% of its full strength. So let's go with that. Ah! See the difference? It's actually sliding now. Watch this. It's going a heck of a lot faster, stronger. It's actually moving on the desk. Before it didn't move at all. Scared to even grab it now. Now that it's at 80%. Huh. Program this motor to move. Alright, I don't think this thing's going to be strong enough. We need to create a torque converter. Huh. For what is the motor? For my laser printer power assist system. So basically, my goal is to have this thing turn a belt connected to the pickup roller of my laser printer, which will aid the pickup roller in being able to turn and scoop up the top paper in the stack of papers in the paper feeder tray. It doesn't have enough strength to do it on its own. In order to solve that temporarily, I had been manually flicking the pickup roller with my finger to try to get it to start turning. Gosh. Well, we need to gear it down, it looks like, because it's all bark and no bite. It doesn't have any force at all. Why not use more than one? Oh, then I gotta create the whole thing again. All the protection circuitry, the diode, the ceramic capacitor, solder it all together, create the custom output shaft, and on it goes. When one motor is always going to be strong enough, but you have to gear it down. They're designed for high speed. They're not designed for high torque. Unless if you torque convert the speed down. So you can either have weak torque, high speed, or you can have high torque, low speed. Not to mention the cost. You want to just throw more motors at it. Not only do you have to do all the circuitry going along with all of that again, and now you have to get multiple buck converter power supplies to power multiple motors now, throwing more and more power at it. It's inefficient. When you already had enough power, if you just converted the existing power, the existing electric, and the existing one motor, which should be plenty, if you convert that torque down. Okay, let's see. If it were turning something big onto something small, the small go faster. If it's turning something small onto something big, the big. I feel like I didn't see this coming. I guess I assumed a motor of that size would be stronger than that. It just feels like it's so incredibly weak. Huh. I just overestimated it. I thought if you squeeze the output of a motor, it's gonna tear through your fingers easily. But I'm not squeezing that hard and it's not even budging my hand at all. Not even a struggle. I got all different size motors. I can use a bigger motor or try to torque convert the speed down. It's got plenty of speed. I can torque convert. I should learn to torque convert. That's a good skill. Very good skill. This motor was made for a four-wheel drive toy. You would think it'd be plenty strong enough, right? Three to 6 volts is its actual rated input. Nominal rated input is 3 volts. Okay. Oh, it doesn't say anything about, it just talks about speed, but not about torque. It's like 5 times 0.5, 2.5 watts. Three times 5, 15 watts. 1200 watts is the outlet of a wall. This is 2. 2 times 100 is 200 times 8 times 6. 600 times 2 is 1200. 120 times 10, 1200. 1500 is a wall. No, about 1200 is a wall. 600 times 2, so yeah, it's like 1/600th the amount of power of a wall outlet. It's just not a real powerful thing. But a motor of that size can power a pretty darn torquey servo motor. But that's being geared several times. Wake up. How much gearing is in a servo motor? Wake up. What is the gear ratio of a motor? Servo. Press return. Stop listening. Adding a gearbox to a servo system helps to achieve the desired load to motor inertia ratio. A perfect inertia ratio of 1:1 is often impractical and in many applications unachievable. Most applications operate well with inertia ratio of 5:1 or 10:1 or even 100:1 or even higher. Okay. We're going to create a pulley system. It's going to consist of little nails and those will thread through little plastic bottle cap holes, which we'll cut out. And we'll create a plastic outer cylinder. So we're going to create like little drums, plastic outer cylinder, which could just be a piece of bottle rolled up and glued onto the 2 drum end caps, and then a hole drilled through the middle, and that will make a little drum. And we have to make a big drum, and then another little drum, and then another pulley, and then that will go to a big drum, and then to another little drum, and then that will go to the belt. So there will be 1 belt, 2 belts, 3 belts, and there will be 1 pulley, 2 pulley, 3 pulley, four little pulley drives, and 3 belts. And I'll draw it for you guys so you can see what I'm talking about. This is how we're going to change our torque. I want to do it this way because I feel that that's the most satisfying way and a great proof of concept for some ideas that I've been exploring mentally, at least. Alright, first of all, check this out. So we could put down a piece of bottle cap, like that, and then we could use a 3D pen to build up a wall here, which we can build up in layers all the way up, more and more, and then we'll put down another bottle cap. So let me draw it from a better angle, because that's a poor angle. So it's going to look like this. And then will come the top bottle cap. And then there will be the bottom bottle cap. Okay. And that will be a pulley, and our belt can come off of that pulley. Like that. Okay. Now, right now we have a motor with a little pulley. Okay. And it's got too much speed, but not enough torque. We want to trade speed for torque. So we're going to go for like a 10-to-1 or something. So we're going to have that thing come right up with its belt to a larger pulley. Which will then be attached to a small pulley, which will then come down and it will attach to another larger pulley, and then it will come out to the final pulley, and that pulley will connect to this pulley, which is on the pickup roller shaft, and then the papers, let's say we have an envelope here, the papers feed in like this, into the shaft. So anyways, yeah, instead of just going direct with a belt coming off our motor to the pickup roller, since the motor is so weak, we're going to convert with a series of plastic pulleys made from water bottle caps. This, if this pulley is like, let's see. We could have it be, let's say 3 times the size, so that's a 1 to 3 ratio. And then we drop over here, we do another 3, so that's 1 to 6 ratio. And then we drop down to here, we do maybe a 2, so that's 1 to 8 ratio, I guess. So it will be 8 times slower and 8 times stronger, which is probably perfect, give or take. Now this is actually what goes on inside a servo with gears. A servo would just have a little thing right here with the potentiometer, and it's normally in a box like that. And then this is your servo horn, which is like, you know, a thing like that or whatever. But we're instead of using gears, we're using elastic rubber pulleys that are under tension because they're elastic. And we're just making little plastic turners, so it will be all silent, no gears involved. It's just a pulley system. All it is belts under tension. More like how a car works with its serpentine belts. So that's how we're going to convert the torque down. And should work fine. In fact, I could 3D print these 2 pulleys. And I could 3D print this pulley too. That would be kind of cool. To just 3D print them rather than try to hand fabricate. But I don't know. We could even just skip this second group like that and just go with the single conversion and then drop back down to this output size. So we just went up 3 times the strength and 3 times less speed, and then drop that down, and then have this one be kind of big, so that maybe that'd be 1 to 6. So I don't know. Some things to think about for sure. There are different ways I can play it, but I think it's pretty exciting stuff. I may have had a slight inkling that that would be a possibility, I think. So let me just go ahead and add this all to my to-do list then. It's a nice skill to have, to be able to convert like this. Doesn't it seem... Oh no. Wait, I'd be an idiot to make the pulley system if I could just use a servo, right? But wait, aren't servos huge? Yeah, but this would be huge too. Once you add it all up. Yeah, but I want to try to stick with not servos. I really wanted to set a precedence for using pulleys. Plus, pulleys have slip. I want slippage, maybe. This is really... It's a tough call. Yeah, I should just use a servo. But I could replace the PWM mechanism and use my setup here. That's the best thing, because the servo gives you the gear ratio automatic. Making pulleys myself, it's just not practical. I don't want to torture myself. We don't need to do it in this case. I don't think it's necessary. Absolutely not. Okay, so let me just go ahead and add these notes then. Wake up. Locate stripped down servo. Get out an MG996R. Press Shift M. Press R. Press space. Servo. Press delete. Press space. And remove its control board and potentiometer and limit stop. And swap our motor protection circuit board into the servo where the old controller board and potentiometer used to be. Making sure to connect the board up to the correct polarity of the motor in order that it turns counterclockwise based on our PWM MOSFET controlling it. Press semicolon. We are going this route to benefit from the increased torque and decreased speed that this will provide. Stop listening. Wake up. Create a simple big pulley and a little pulley coming off it. So that we decrease speed by 5 times and increase torque by 5 times as a trade-off. Press delete. And also include, guys, I am going to make the pulley system. Stop listening. Alright, so that's the next step for the laser printer, is a pulley system. Just like the one I just drew, I'm going to do it. What have I gotten myself into here? Unbelievable. It'll be fun though. You know, we might be able to get it done quick. I hope so. My fabrication skills have to continue to get faster, you know. That's important. It is the project that never ends after all. I guess it's appropriate for us to be extending the scope again. This just keeps getting more crazy. Good grief. What have we gotten ourselves into? I went so past my quitting time That that I'm delirious. And I'm gonna have to skip dinner and everything. I'm going straight to bed. That's good though. I'll take that over, I don't know. Every now and then I should get so lost in my work I go to bed late. That's a good thing.